Hi, my name is Pinsung Ku, a PhD student from the Hybrid Body Lab at Cornell University. And today I'll be presenting our work titled Patchel Deformable Woven Patches for On-Body Actuation. Patchel exploits a woven patch form factor to enable diverse movement-based interactions. The Patchel interfaces are uniquely detachable and relocatable soft actuation units that can be sewn or attached to clothing or skin. This work is inspired by researchers that have been pushing the boundaries of expressive interactive textile interfaces. However, there is in general a trade-off between two directions of practice. One end of the work fabricates specially designed garments for single actuation. Through a longer period of fabrication, it can achieve a conformable slim form factor. On the other hand, building detachable actuation parts can realize faster fabrication and support actuation effects more diversely. But the bonding between the fabric and the typically non-textile device often brings undesired rigidity and thickness. In this work, we seek to find a balance between the two trends, where we can approach an underexplored textile practice, woven patches. We extend the concept of patching from mending and repairing into a new role, textile deformation. We created morphing woven patches that are flexible and conform to the clothing or a human body. The versatile functions and detachability the patches provide are also ideal for quick prototyping or testing. Patchel is built upon several critical design choices we referred to previous literature, including the fabrication method, the actuation mechanism, and the materials. The first critical design choice is the fabrication methods. Techniques such as digital embroidery or 3D printing construct circuits with the conductive material over the base fabric at a surface level, while textile construction approaches, such as weaving and knitting, allow the material integration takes place at a structural level. Among the options, we choose weaving because of its intersecting structure that makes embedding material inherently simple. In terms of actuation mechanism, we have seen works utilize mechanical actuations with motors, pneumatic actuations with expandable inflation channels, and also biological mechanisms that utilize the natural response of living organisms. However, these approaches are either limited by the size, mobility, or difficult to program the control. In contrast, we found shape memory alloy to be especially promising for on-body deformations due to its energy efficiency and flexibility. Different forms of SMA products, such as a spring or a wire, can be integrated in various form factors to achieve diverse interactions. Unlike previous work that often targets a single SMA actuation mechanism, we successfully integrated three types of SMA products to the woven patches to enable a wide range of morphing effects. Next, I would like to talk about the implementation of Patchel system. We implemented three basic actuation primitives: bending, expanding, and shrinking. Each primitive was built upon the choice of SMA actuators and customized woven substrates. For each primitive, we also identified the aggregation parameters to extend the actuation library of Patchel. First, we have the bending mechanism. We used the SMA wire for contraction and wove a stiffer fabric on the two sides to constrain the deformation while anchoring the SMA. The central region woven with silk is softer, and the section of SMA floats either above or below the softer region. Since the stiffer region on the sides restrains the SMA, the shrinkage concentrates at the flexible region in the middle and pulls the softer part of the fabric on both ends. The fabric would then be bent in the direction curving toward the SMA wire. To create more complex deformation, one can weave multiple softer regions to divide the patch into sections in a one-dimensional or two-dimensional space and control the bending direction between each section by manipulating the SMA wire integration. The second mechanism is expanding. In reverse to the bending mechanism, the shape memory effect of the SMA wire can be used to expand the fabric from a flat 2D shape to a 3D structure. We adopted the double close weaving technique to create an expandable structure where the expansion happens at the bend joint. When actuated, the SMA wire would tend to recover from the bend status back to a straight line, which expands and opens the folded double close structure. In addition to the open-close patch design, some other representative designs of the expanding patch include the tube shape and egg shape, where the top and bottom layers are connected on different locations. Finally, we have the shrinking mechanism that creates a much more prominent shrinkage across the whole fabric surface by leveraging the SMA spring. We set up supplementary works with copper wires. A tiny ring structure was designed to trap the SMA spring for solid electrical connections, as shown in the figure. One can integrate multiple SMA springs to increase the pulling force. Adding webs of copper wire can also allow more segment controls of the SMA spring. With all the designs we identified in the implementation, we conducted a workshop study to gauge the feasibility of creating personalized morphing patches and to prop perceptions towards the patch form factor. The first study result is Brain's project, an expanding patch for opening the third eye. Ren is a textile artist with 17 years of weaving experience. She expressed her love of integrating emotional elements into her textile practice, aiming for the moment when humor and vulnerability intersect. The patch is woven in a one-margin double weave, with the band joint of SMA connecting the two layers, referencing to our expanding patch design. After weaving a double close structure, she then interwove the eye pattern with black yarn. Next, we have Kendall's project, wave bending patches as dynamic fringes. Kendall is a textile studio assistant with 5 years of weaving experience. They integrate abstract, colorful patterns into weaving patterns. Kendall chose the bending primitive and implemented the wave shape aggregation method. Besides, they customized their patch through tapestry weaving with colored cotton yarns for aesthetic purposes. The third project is done by Blair, a PhD student in apparel design with 1 year of weaving experience. Blair prioritized function over aesthetics, and the function she found missing from the clothing was the self-fitting capability when needed. She selected the shrinking primitive for the strong force it can provide. As shown in the video, she applied the patch behind the back of the shirt, which could create a better form-fitting silhouette for professional contexts. Last but not least, we have Alex's project, a tubular expansion patch for surprising outcomes. Alex is an engineering and design undergrad senior with 1.5 months experience in weaving. She was interested in designs that were extreme, absurd, so that she could be surprised by the outcome. She attached the patch to a mask, which would open and close like a mouth. She also tried locations such as under the upper part of her hair, full expansion in volume, and to her jeans as a belt loop that could expand to make it easier to loop in the belt. Alex experimented playfully with various patch deployment locations until reaching the ideal setup for each location. During the workshop study, we observed that the temporary and quick yet sturdy reattachment of the patch interface allowed playful experimentation with movement on diverse locations. The participants also found the gradual shape change afforded by SMAs to be surprising, but they resembled deformations typically seen in existing garments. While some participants prioritized the effective aesthetic expression of their patches, others designed for resolving practical clothing issues which could benefit from the moving patch. Lastly, our participants ranged from beginner to expert weavers, yet all were able to pick up the patchwork primitives easily and successfully created their patches. For discussion, we acknowledge that actual unclosed deformation is affected by various form factors, ranging from the tension of the body, deployment angle, to fabric structure. A more comprehensive test with exhaustive conditions is required to understand the exact unclosed performance of patchwork. To support actuating multiple patches, we plan to build a custom PCB board to address multiple powering requirements and realize an untethered system design. In our workshop study, we observed that the most time-consuming aspect of the fabrication process is weaving the patches. While the woven interfaces can also be fabricated through digital jacquard looms for scalability and speed, this does trade off the real-time creative experimentation offered by hand weaving. However, it could serve as an option for scaling up a finalized design for broader usage. Above all, I would like to conclude the project with the following highlights. This project is supported by the National Science Foundation. Thank you for listening.